Hello, welcome to another episode of Rustacean Station. I'm your host, Alan Wyma. Today I'm with Tiemoko Ballo, who is the author of High Assurance Rust, which is a book introducing you how to write performance software using justifiably trustable Rust. I believe that's the best way to say this. Let me know if I'm saying that wrong. Or maybe you can just give us your best way to answer this. Go ahead.
Sure. So it's a book about building secure and robust software in general to the furthest extent possible using open source tools. And the term high assurance typically refers to trustworthy software, which means we have some processes or tools in place that gives us confidence in both the functionality of the software and its overall security.
That's really a mouthful. Do you have a smaller, simpler way to push it? Like if you were to explain this to your family, how would you tell them the best way to understand what you're working on?
Sure. So I would say that it's about building software you can trust.
That's a perfect pitch right there. So what's the point of that, right? Because we're having more and more of this kind of idea, which is kind of weird. So if you have a type system, it's already something that you can trust a lot more, right? Because you know what's going to be coming out. If Ferricine is some work on something kind of similar, I believe. We've been talking a little bit about this kind of offline. And now you have this book, right? So do these things really relate to each other?
Yeah, so there's a lot of momentum in the Rust community for the usage of Rust in safety critical systems. So currently Rust is used in mission critical settings. So that means things like high performance distributed infrastructure, financial services, things where the correctness and the uptime and reliability of software is tied to the business. And what Ferricine and other related projects aim to do is move Rust into the domain of safety critical systems. And the idea there is that cost of a software bug could potentially be loss of human life. So correctness is extremely important. And I'm glad you brought up Rust's type system, because that is actually a form of what we call static analysis, which is a way to reason about all executions of the program and get really strong formal guarantees. So Rust's memory safety guarantees actually come from this type system.
Yeah, maybe we could talk more about this. So there's safety critical and mission critical, right? So what's really the difference? To me, what I always want my stuff to be safe and kind of, I guess I would define mission critical as like it has to be running or it has to do something by a certain amount of time.
Yeah, so mission critical, I would say, I don't know that there's a universal definition, but the way I think of it is the uptime of the service and its correct function is essential to the business. So if the service goes down, the business is hemorrhaging money. Whereas safety critical systems, usually you're talking about what are called cyber physical systems. So they're systems that interact with the outside world or maybe control a important physical process. And in a safety critical system, the cost of a bug doesn't just mean a service downtime. It could mean actual catastrophic events up to or including the loss of human life.
It's pretty crazy stuff. Yeah, things like pacemakers, things like that, right? We have to have the rhythm going, and if you're off, then somebody could really get hurt, right?
Yeah, pacemakers, autonomous vehicles are another one that's kind of getting bigger now. Anything where there's including aviation or things like that.
Okay, but how can we actually develop software in Rust and have this, what you call high assurance?
Yeah, that's a good question. So I want to explain the book's title a little bit because it seems that some people or most people seem to like it, but there are a few people that say, well, Rust is not yet certified for usage in safety critical systems like a language like Spark Ada, for example. And that's part of where the Ferricine effort comes in. So I guess what I mean by high assurance, if I can explain it a little bit, is there was a DARPA research program, I believe it was from 2012 to 2014. And DARPA, for listeners that may not be familiar, is one of the most famous research arms of the US government. So their claim to fame is inventing TCP/IP, the core technology that powers our modern internet. And in about 2012, they ran this program called HACMS. And HACMS is an acronym. So in government research, I feel like you have to have an acronym or you're not getting funding. It seems like we really love them. So HACMS stands for High Assurance Cyber Military Systems. And that program looked at the applications of formal methods to cyber-physical embedded systems. So the idea was, can we use some kind of principled and mathematically rigorous approaches to gain more confidence in the functionality and security of important software? And the program did a range of things. It's not a program that I've ever worked on. I'm just kind of familiar with it from reading about it. But one of the particular innovations that stood out to me was there was a team that invented a DSL. A DSL is a domain-specific language. So it's a programming language, but it's not general purpose. It's kind of intended for a very specific task. And their DSL, which was kind of functional and had a Haskell-like syntax, had two important properties for the purposes of being high assurance. The first was that it was memory safe. So it actually transpiled to C, and then the C compiler would take that and generate the machine code. But you had this guarantee that the output C code had memory safety properties. And then the second important feature is that it did not use dynamic memory. So it only used stack memory. You don't have a heap, so it has certain robustness benefits. You're not prone to fragmentation. Your worst case execution time is not impacted by the state of the heap. So essentially, what they called high assurance was the special DSL for embedded programming that had these two properties. And when I saw this, I immediately thought, well, this just sounds like safe Rust with the no standard attribute, right? So if you're not using the unsafe keyword, you have memory safety guarantees. And if you're using no standard and not pulling in alloc or none of your dependencies use dynamic memory, then you also get that stack guarantee. So to me, it was kind of inspiring and exceptional and really just wild that what was considered the forefront of cutting edge technology in a government research program not so long ago is now, some of the features at least are offered by a commercially viable and widely used language that's getting more and more popularity. So I think I forgot your original question a little bit. Does that answer the high assurance portion?
Yeah, it does. I mean, the thing is, some of the stuff is really hard to kind of make it into a very like simple language about the high assurance, right? And sometimes some of these terms kind of bleed into each other, right? Like with Ferrocene, it's all about, how can I prove that the code I write is going to generate the right, I guess you would call it machine code that does what I want it to do, right? Because
Yes.
you can't really guarantee that necessarily, right? I mean, because nobody really wants to go in there and see, is it actually generating the right assembly code or this kind of stuff, right? They just want to write at a high level and compile it and be done, right? But fixing one bug is like cutting off the head of a hydra. You can get two more heads that pop out, right?
Yeah, so I'm glad you brought that up because that's actually a very important piece of certified compilers is the certification of the backend to say that the actual assembly generated the semantics of that machine code are going to exactly match the source code that the developer is reading. And that's definitely a part of assurance. That's not a part that is currently handled in Rust. To the best of my knowledge, the LLVM backend used is not one that is verified. But actually, in the grand picture of what we consider high assurance systems, there's one school of thought that actually says we're going to completely remove the compiler from the chain of trust and just test the binaries themselves. So we're going to look at the executable code, what the CPU fetches and decodes and executes instructions from directly. And in that case, you don't actually need as much of that verification if you're just testing the binaries and not mapping back to source. A lot of interesting kind of components and challenges in the space. And my understanding of the Ferrocene work is that right now their main initiative is actually to create a specification for the Rust language. So something that would make it feasible to implement an alternate compiler, whether that was one that had assurance properties or was just experimenting with some feature. If everyone is working from the same standard in terms of compiler developers, then that's something that's enabled.
Now that's where things get a little bit tricky because it's like, wait a minute, you mean there's no standard behavior? If I do this thing, it's not going to do that thing I think it's going to do? You know what I'm saying? Like what you just said, like that's like what immediately comes to my mind. It's like, wait a minute, then how can I be sure that if I say, 1+1 and then set it equal to something and output it, that it's not going to be 2, right? That seems a little bit scary, no? If you're saying that there's no kind of standard way, or am I misunderstanding what you're trying to say?
No, I think your understanding is pretty correct. That's actually a great question. So right now, the state of things in Rust, and I guess maybe it makes a little more sense to contrast that with C. So because C, as you know, is systems programming language and one of the main places where you want to use C, where C is the only option because you can't have garbage collection, you bare metal code. Those are the kind of places where you want to use Rust. In the C world, there's this ISO C standard. And the idea there is that it defines the language from the perspective of an abstract machine. So it means that essentially no matter which compiler you're developing or which architectures that compiler targets, there's one universal description of what C's behavior, including what we call undefined behavior. So there are certain cases where the standard can't impose a rule, and that gives compiler developers the ability to do optimization. But I guess we have this baseline with the C standard. And going back to your original question, it's not so much that we don't know what Rust will do. It's that we kind of use the existing implementation, the mainline Rust compiler, Rust C, the open source one. We use that implementation as a specification. So we say that what Rust does is whatever this particular compiler does, but we haven't been able to yet formalize that this is what the Rust language should do in the general case, regardless of which compiler is being used.
Yeah, now that you mentioned, there's a lot of programming languages that don't really have a say like a reference compilation. They just say, well, the unofficial official way is just whatever this thing does. Like for instance, there's the Ruby project, and they say, okay, whatever Matz's compiler, whatever Matz's what do you call that output does, that's what Rubinius wants to try to copy off of. That's kind of the best idea that I can think of. So it's like, okay, we write this kind of code and it's going to output this kind of binary. When we run it, then we should expect that the implementation matches kind of whatever is being pushed out by the Rust up installation method. Is this kind of the way I can think about it?
Yeah, yeah. I mean, and it's not necessarily a bad way to do things because I think there's actually some advantages to having a centralized implementation. And like you're saying, if we are all kind of in agreement and the behavior is reliable, then it's potentially a fine way to proceed. But where we get into challenges is when you're talking about certification for safety critical or domains where there's a bit more kind of onerous for regulatory compliance. In those cases, having documentation to point to, at the very least, even if you make the argument that you're fine without the specification, it gives you kind of a paper trail to be able to prove and reason about certain things.
But if LLVM is able to somehow kind of do some of this, because you're saying that there's no like reference implementation for when LLVM outputs the final binary, is that what I also heard you say earlier?
The LLVM is the backend for Rust, the Rust compiler to do code generation. And I'm not familiar with specification efforts around LLVM specifically, but what I mean is that there's currently no specification for the Rust language itself.
Yeah, but I was just thinking like if you could say, okay, what I understand about LLVM is that you spit out the bytecode and then LLVM will take that bytecode and output the proper machine code based on the architecture. Is that the proper understanding? I think you probably know about this more than me.
Yeah, so it's very close. So instead of bytecode, it takes as input what is called an intermediate representation. So this is it's almost like an assembly language, but it's designed to be amenable to compiler passes to generate efficient assembly language for specific architectures.
So that's why I'm wondering, like, if we could somehow, like, if LLVM went ahead and somehow said, okay, if you give us this type of IR, we're going to output this type of, have a specification, and then Rust could say, okay, we're going to do that, but we're going to stop at the IR. Couldn't you put that together and also have some type of high assurancy to it?
Yeah, yeah, that's a great point. So IRs, whether that be LLVM's IR, Rust's MIR, they're kind of this great abstraction for a lot of compiler work. And one specification approach, like you're saying, is you could have something that maps the source code to the intermediate representation and say that that mapping is correct. And then you could have something that maps the intermediate representation to the generated assembly and say that that mapping is correct. And if you have both of those two things in the chain, then you do have a high degree of assurance in that sense. But what I think of when I say high assurance is really more with respect to Rust's memory safety properties. So this is kind of agnostic of whether a specific compiler is verified.
Yeah, so this stuff about high assurance, safety critical, memory critical, safety, memory safety, my mind's starting to get a little bit crazy on me right now. Maybe we could talk more about kind of like really what you're talking about. So without the formal specification, right? Are you saying that we should be looking more at the final output when you actually run it? It should be doing. Is this the way you're looking at it?
Yes, that's one approach to assurance testing. So some industries, that's just the way because of their model of trust, they have to verify the actual artifact that will execute on the CPU and say that regardless of what compiler it came from, we do automated manual testing of the binary itself because it's the closest to ground truth. That's not all safety critical industries. And I guess specifically what I mean by assurance is really provable guarantees of memory safety, which in the systems programming world buys you a whole heck of a lot of confidence that your program will both perform correctly and be reliable in terms of uptime and also be more resistant in terms of security breaches.
Okay. And I understand that the way that Rust kind of memory safety works is that you can get a lot of that out of the box, right? And you must know about this quite a bit, right? Can you start to explain a little bit about how that actually works? Because I think as much as most Rust programmers probably do is that they fought the borrow checker, and then after they stop fighting it, start working with it and start kind of listening to it, then they kind of just say, okay, well, I got my memory safety guarantees. I'm good. I'm done for the day. I'm not going to get, heartbleed or something like that. But what is actually going on underneath? You're actually able to start to explain some of this, right? Because this definitely leads into it.
Yeah, so that's a question of breaks. I'm more familiar with that side of things than the compiler internal side. Developers have this experience of fighting the borrow checker. And what I want to say about that before I get too far into memory safety is that the value there is you're actually part of a human in the loop verification process. So when you can appease the borrow checker and kind of compile your program and it's free of errors, then you have a static and formal guarantee that there's some caveats here, but theoretically, it means there will never be a memory safety bug ever in that particular program, assuming that your dependencies also adhere to that same level of strictness, or maybe you have no dependencies. So the fighting is, it can sometimes be rough, and there's an initial learning curve that, people definitely have to do a little bit of work to overcome, but it's also very close to formal methods or being able to do a proof in a way that I think is more accessible to a lot of engineers in the day-to-day than some of the alternative approaches. So as far as memory safety itself, how that works in Rust, in order to understand that, we have to be able to bin memory safety bugs into two classes. So we call these, usually in the research, spatial memory safety errors and temporal memory safety errors. So I guess I can explain each of those a little bit separately. So spatial memory safety errors are what you think of when you think of a classic buffer overflow. So you've allocated a fixed size array on the stack, you're maybe taking some user input, you're writing some data to that array. And if there is no bounds check, like as is the default in C, then you can write values past the end of that array. And that's very problematic for a variety of reasons. One of the main ones is the way that stack frames are set up in most architectures. You have something called a return address at the top of the stack frame. So one way to gain control of a program, and I don't need to go too much down to the weeds on this particular aspect, but essentially if you can write past the end of an array, you can write what is like kind of a control flow primitive, and then you can tell the CPU where to go next, which is how attackers gain control of a program in this kind of exploitation process. But the idea with the spatial memory safety enforcement is that the Rust compiler actually has to do that at runtime. So it inserts these bound checks, which have the potential to cause a panic. And it does that whenever it can't prove that the accesses are safe. So if you're not using iterators, for example, and you're using array-based accesses, the compiler actually has to insert additional code to verify that you're respecting the length of the buffer there. And a current weakness of that is what's called stack safety, which is it's a little bit different. Does that make sense so far?
Yeah, I didn't even think that about the runtime. I do remember hearing from somebody that there is a very small runtime within Rust, and that's not completely runtime free. So this would be part of that very small runtime, right?
That's an interesting question. I think bound checks might not be considered part of the runtime solely because if you are compiling Rust for a bare metal target where, your code, there's some vector table, you jump directly to your code and there's really no additional supports, not like on a traditional operating system where you have set up and tear down tasks before and after process runs. I think I would be tempted to say that the bound checks are just part of the program itself and wouldn't be considered part of the runtime. Now, if you're talking about how do you catch the panic, so what do you do when the bound check fails? That is the job of the runtime, because if you don't have an operating system, your options for handling that are low.
Okay. All right. This is slowly starting to come to me. It's definitely a topic I'm interested in, but I feel like I don't have enough kind of understanding, but you're helping me to understand a lot more. Okay. So actually, I didn't even know about that, but that makes sense that there's like you said, that panicky stuff that gets inserted in, because I am aware of that there is some of this kind of stuff, right? So that gets inserted to you free of cost, but actually there is a cost to actually run that, right?
Yeah, so there is some performance cost, and this is one reason why people may sometimes choose to use unsafe. If you really, really trust that your program will always do the correct thing with respect to bounds, you can actually use a function to do accesses without that check. The performance cost is actually relatively minimal, and the compiler can avoid it inserting the check in a lot of cases, like when you're using kind of idiomatic iterators. So it's not that bad, especially relative to what the consequence of not having that check might be, because then you get into the memory safety and exploitation. But I did, before I lose track of it, also want to mention that's one aspect of memory safety, and that's how the Rust compiler enforces it. But the main one, or the one that I'm kind of more excited about and I think is more interesting from a technical perspective, is how Rust addresses temporal memory safety. So this goes back to what you mentioned earlier with the type system. So we said that spatial memory safety, it's kind of, it has to do with space in the sense that there's a buffer and it has a fixed amount of space. But temporal memory safety has to do with time. So it has to do with whether or not a reference, usually to some object, is in a correct state. So the kind of bugs that you get with temporal memory safety are things like use after free, where something has already been freed, it's no longer in a valid state, it could be arbitrary data, but you treat it as correct data. It's very bad for a range of reasons. Or double free, where you've, in a language where you can manually manage memory, you freed a pointer and then you free it again. And that actually breaks kind of the invariance of the memory allocator and leads to security exploits. Same with uninitialized values. It's like another temporal memory safety issue. So that's where the type system comes in. And that's where Rust is able to use kind of advanced static analysis to reason about your program and prove that any reference at any point in the program is always valid. And this is a big part of what the borrow checker does. So when you're fighting the borrow checker, what you're actually doing is you're helping the compiler prove temporal memory safety properties.
Okay. It's interesting that I do remember hearing about temporal and spatial, but usually I think about that in actual human brain memory, but I never thought that they would actually be using these terms for computer memory, but I guess it makes sense. It's both is called memory, right?
Yeah,
So
it's funny how many like parallels there are between human memory and human cognition, the way computers work, at least at a very high level. I'm not a neuroscientist. I'm not familiar with the deeper level, but I did hear this quote once that we kind of make tools our own image. And that's always stuck with me as something that seems to apply to the way computer systems work, at least superficially.
yeah, I think it also makes things easier to discuss, right? If it's something kind of relatable to you. So is it temporal, right? That's the one that's time-based, right?
Yeah.
How does the temporal actually relate to the high assurance? How can you like make sure that you have a program that's really trustable when you have some temporal memory?
Okay. So I really like this question because the kind of the answer I would like to give is that related to high assurance, you have the ownership system enforces throughout an entire code base automatically, accurately, and regardless of the size of the rest code base, the concept of ownership, and to make sure that ownership rules are never violated. So if you think about what the alternative is, we have languages like C and C++ where ownership are very much concepts. So ownership has been a concept in the C++ community for a very long time. It's not unique to Rust in that sense, but the difference is that when you're writing C++, the burden of enforcing ownership rules is on you as the programmer. So you have to make sure that you avoid these bugs like use after free, like double free, like using uninitialized memory. And there are some patterns in C++, and there are some best practices that make that easier. But at the end of the day, the situation is for software assurance is that we have to have very, very skilled people that are aware of C++ at a deep level, all the kind of gotchas and the caveats of the language, have read the standard, understand undefined behavior, and they have to repeatedly produce high quality code, get the code reviewed to find all the potential errors, including kind of errors of ownership invariance and temporal safety errors. And then once that code goes through a review process, there's still some amount of defects because humans are fallible, unlike compiler analyses. And which actually compiler analyses can be fallible. There can be bugs in the Rust compiler, so I should probably caveat that. But there's a huge burden for actually testing that code, then dynamically doing all these checks to get the same assurance properties that the Rust compiler proves for you for free and immediately out of the box, so long as you're compiling safe Rust.
But we get that because of like things like the borrow checker, right? But how do we actually know the borrow checker is actually working properly? The borrow checker itself could also have some problems.
Yeah, so that's another good question. So the security world, you have this, I've heard this metaphor turtles all the way down, and now I forget the source. So I probably should have brought that up because I can't fully explain it. But the idea is that you have to trust something at some point, right? So, there's got to be some foundation, and you have to start with the assumption that this particular component, we usually call this the TCB or the trusted computing base. You say like, this is something that I can rely on. And then when I build on top of this thing, I'm able to have confidence in what the results are because I rely on this one thing. So in the Rust world, that is the type system. And there has been work in the formal verification of Rust type system, academic work. And I think from what I understand, and I'm not an expert in that domain, it has been very successful, but it's still early. There's still a lot of work to do. And what I will say is that when we talk about any kind of formal verification, we also have to acknowledge that the Rust compiler code base itself is a very large code base that thankfully changes frequently, right? We get new features, we get bug fixes, there's RFCs, there's new contributors. And when we talk about formal verification of Rust type system, it does not actually include somebody working with a proof assistant and saying that every single commit maintains some properties. So it's not a perfect like end-to-end chain of trust, but we do have a high degree of justified confidence at this point that is correct, that those analyses are correct. So when we build programs using Rust, we can be sure that they don't have this particular class of error.
This kind of reminds you of when I took I forgot it was discrete math or something like that, where like you would have, there's like one, what we call like, I guess, give me kind of proof, where it's like, you don't have to prove this thing, but this thing that we know is always going to be true. Now take like point A, and I want you to prove that point like X is true. And you have to like literally say, okay, well, if this is true, then it means that this is true. And if that's true, then that means that this is true. And you have to kind of build your way all the way up to point X from, you know what I'm trying to say, right? I think you probably also took the same course as me or similar one, this kind of logic proofing, right?
Yes, yes. I did take discrete math a while ago, and I do know what you're referring to. And it's a very similar situation. And actually, as kind of an interesting segue, if you don't mind me using that as a segue, the kind of logic that you learn in discrete math is called first order logic. And this is like, if A implies B, then you C, like, that was not the best description. But what I'm trying to say is that what we think of as like the kind of truth table discrete math, the branch of logic that falls under is something that is relatively comprehensible, and most people that complete a CS curriculum are somewhat familiar with. And where this ties into Rust and high assurances verification is that there are actually some very exciting research tools that I plan to dig into later in the book and cover that let you do something called deductive verification of Rust code. And how that works is, so when we talk about memory safety in Rust, that doesn't say anything about the logical correctness of your program, right? So you could have a memory safe program that implements the wrong algorithm and produces the wrong output. In a safety critical setting, that could be catastrophic, right? So you could have a memory safe program that is actually kind of low assurance in the context of what it actually does. And deductive verification tools are a way to help you with that, in the sense that for every function that you write in your program, you can specify preconditions and postconditions. And then the tool in the background uses techniques called SMT and SAT solving, and actually proves that if you treat these pre and post conditions as a specification for your function, that the logic of your function meets that specification. So your function is correct with respect to what you've specified. And back to first order logic, these pre and post conditions are written that logic, which looks a lot like Boolean operators that you're used to in an if statement. So it's something that is actually fairly usable for average programmers.
Okay. Yeah, I think programmers definitely can understand true and false, but kind of adding those things up together to make something really, really complex. Like I took comp sci, I think they call it computer organization, where we really went from gates all the way up to building a whole on CPU. Like, yeah, there's a lot you can do with binaries. So I can imagine that this kind of proofing really you can get quite complex, right? This kind of idea.
Yeah, absolutely. You can start with simple primitives and kind of build up to very complex specifications.
Okay. And through these kind of proofing, right, then we can start to get to more about your book, right? So we build upon these proofs to then say, okay, because of these things, that's why we can write code that we can justifiably trust. Is that correct?
Yeah, so the goal of the book is to say, how can we build the most reliable, the most trustworthy and secure software possible using open source tools? So the book purely covers open source tools. So the deductive verification, that's one set of tools that I'm going to plan for later in the book. And the tools that are currently covered in more detail are the Rust language itself. And also the open source library that the book is based on. I use a technique called differential fuzzing, which isn't a formal proof, but has some advantages that could potentially go into as far as ensuring the reliability or giving you confidence in the reliability of your application.
I like that you do go over fuzz testing, which is fuzz testing different than property-based testing? Or are they similar?
Yeah, so they're pretty similar in that both of them what we call a stochastic process. So they use randomness. And I guess the difference is that in property testing, you have a little bit more bounding. So you're actually writing in your test harness, you're constraining what the range of valid inputs is, and the property tester is picking from that range. But with fuzzing, you actually really, really want to give the program invalid inputs to put yourself in the shoes of an attacker and say, can you handle this thing that you do not expect? And so in that sense, the input space is much larger, and the process can be a little more automated depending on what kind of fuzzing you're doing and how your fuzzing is set up.
Okay, that makes sense. I guess it's different than what I heard one time called Chaos Monkey. We just start throwing random crap at something, hopefully, or that sounds very similar to fuzz test. You just want to just pummel stuff with random data.
Yeah, the similarity is that you're essentially testing the resilience of a system, or kind of like how reliable is this? Or so in fuzzing, it's kind of the input path. In chaos testing, you might be taking down specific nodes and making sure that the service is still up or that the infrastructure can reconfigure itself or reroute. So I think of chaos testing as more of an infrastructure level thing where you're simulating unpredictable downtime events for that availability property. Whereas in fuzzing, you're testing for both availability and overall security by feeding it inputs. So both are forms of stress testing, essentially.
Yeah, it's quite interesting because I do remember, I've heard the story and I'm pretty sure it's pretty true, like when people who are working on Erlang were like trying to do some testing on it, how resilient it is, they were literally ripping wires and ripping hard drives out of like these big servers to see what would happen and see if you can actually recover stuff, because like, things go down, like, well, how do you handle that? You just restart it, or you have to somehow say, okay, this part of the system's down, okay, let's cut that at this part, and then like we can try later to turn it back on once things look better. And then, but we have to still keep running, right? Like there's no reason that like people try to develop their system where it's like, okay, you can hit the home page is fine if we don't have access to the database, but if you try to log in, then we should definitely throw an error or let you know to come back later on. That kind of balanced resiliency.
Yeah, and that's kind of resilience that you're describing is a very important part of assurance. Say like military cyber physical systems, you actually sometimes have two separate computers. So if one goes down, like if the hardware totally fails, there's like another one that comes online and starts taking over tasks because, it could be something like an airplane where you don't want it to crash, right? So you actually have a full backup. In some cases for assurance, these backups are actually implemented with what's called clean room design. So they are coded off of the same specification. This is something that's called N-version programming, but the implementation is completely independent. So what that means is whatever bug you hit in that primary, you're unlikely to hit the same bug when the secondary comes up, because if you give it the same inputs and it crashes in the same way, that wouldn't be very good, right? Then you've killed both of your machines. So a lot of the time when you have these redundant backups, you actually want them to be significantly different internally to make sure that they survive when the primary fails.
Sorry to kind of side talk about some interesting thing, but it kind of reminded me of, sorry to talk more about Erlang and stuff, but I remember listening to this one story where they had this machine that was always running for like decades or something, or years, and they never even switched it off ever because it was super critical and it was just running and you could just hot code upgrade everything. But they reached a point where they could no longer hot code upgrade it, and they actually had to flip it off and turn it back on. Well, they planned everything. They had the downtime window. They had everything ready to go. They tested it several times on another machine. So that way, obviously, if you're going to do something like this, you want to make sure you test it on something similar. Everything went fine. But the day of when they went to do it to the main machine, it just stopped. It just wasn't working at all. Nothing was working. They couldn't reboot the machine. Well, what it turns out in the end was actually something that I think nobody would ever think about, was there was actually a piece of dust that actually went the read head of the hard drive. And because of that, it couldn't read the disk drive. So this kind of problem, I mean, it's really difficult to test and really hard to figure out. I can see your smile right now. It's a very interesting problem to have, but like, how can you have something like this? It's really difficult to figure out even.
Yeah. And that goes back to what you said earlier about we have to trust something, like we have to draw the line somewhere. And usually from a software assurance perspective, when I write code, I don't assume that there's going to be dust in the hard drive, right? So it's just kind of outside of the domain I'm trying to reason about. So I operate under the assumption that hardware will work. And that's not always a correct assumption, right? Because there's a lot of people hardware engineers that think about that stuff more. And that reminds me, and I don't know the exact story, but I think the reason we use the term bug to describe an error in the logic of software is because there was some ancient computer system where there was actually like a live bug, like an insect that got stuck somewhere in the wiring, and that caused the system to go haywire. And that's why we adopted that term. So
yeah, something like that.
Unplanned
that was Grace Hopper, which is actually in the similar field as you, right? I don't know how much you can talk about that, but yeah, Grace Hopper was actually, I mean, the nice part about these, like, I kind of wish I was from a long time ago, because you can really understand a lot of what's going on today, because like I said, the stuff is kind of built on each other. But she was kind of born in a time when there was nothing really around there, so she made a lot of stuff, right? Same with that word bug. Like you said, it literally was a bug that was in the system, and I think it fried it or something like that, like you said. But she's the one that came up with that term. Yeah, so now we always have that term around because of her. I just wonder, like, what if it was like a toenail clipping, right? There's a toenail.
Yeah.
You got a toenail in your machine or something in your software. I'm just wondering, how would that even look like? How would life be if it was something else?
Yeah, I want to say I'm glad it wasn't a toenail, just because that, to me, that's a little more, that makes you cringe a little bit. Like, a bug is less gross than toenails.
You've already been desensitized, right? I mean, you ask some other people, they may think that bugs are disgusting. So, for instance, I got 2 Chihuahuas, and one of my employees, he gets freaked out whenever he sees a dog, even my little Chihuahuas. So I still can't understand how the heck that works. I mean, they're really like, very small. So, what freaks you out may not freak other people out. So, yeah, they're just words, right? I mean, we can talk about like male, female ends for connectors that we used to say a long time ago, right? You put together computers when you're younger, right? Master, slave, this kind of stuff. I mean, now it's not proper to say that, but You just become desensitized to these kinds of words because it's just the term to use. I mean, what else can you say? I mean, it's got to be a primary, secondary. I guess you could say that, but for some reason, master slave kind of took off.
Yeah. I mean, the terminology changes over time. It's the same as now we have the main branch on GitHub as opposed to the master branch. So.
Yeah, that's another one too. Like these kind of terminologies change, right? And so maybe you're saying that it's time for a change. For maybe we're not respecting bugs enough. We need to come up with another word.
Yeah, so I like bug. I'm used to it just because I feel like another part of this is once something becomes socially widely acceptable, then you have this shared language. So I think at this point, bug is so, almost every developer knows what that means. So it's kind of useful from that perspective. But where I do think we have the opportunity to make a change and make an improvement is just using principled techniques and processes to reduce the amount of defects or bugs. I guess defect is another word I like as well. We can reduce the bugs in software we ship. And that's, I think, what the focus of the book is, and also what Rust in general is just so amenable to just building more correct software.
Yeah, actually, I do want to go back a little bit before we run out of time about like your history, right? So, yeah, you have a very interesting history, right? Because you're in the US, but you're not originally from US. You got a very interesting background about how you got into programming. Can we talk a little bit about that?
Yes, definitely. So I would like to cover my background a little bit because people might be wondering, like, what is this guy's qualification to be writing a book? So let me start with how I got into programming. So that was through a bit of random chance, actually a lottery system. So I'm a first generation immigrant. And before the Trump administration was unfortunately removed, there used to be this program where if you were a legal immigrant with a work visa, you could apply for a green card lottery, and then you'd be granted permanent residency, and eventually you could become a naturalized citizen. So my family is from the country of Mali, which is a beautiful country in Northwest Africa. It's in sub-Saharan Africa. And there are not a lot of immigrants statistically every year from Mali to the United States. So the lottery is actually weighted by country of origin. So while I was young, while I was a dependent, won that lottery, and that's how I became a US citizen. So where this gets into programming is I have been working in cybersecurity for almost a decade. And I started out in a field called incident response, which is a very exciting job, but it doesn't involve software development. And I actually wanted to go back to graduate school to get more into specifically systems programming, kind of low-level development. And because I had a US citizenship, I was able to apply for this amazing program called the Cyber Core Scholarships for Service Program. And this is a program that, unlike the Green Card Lottery, is still going today. And it's also not random chance, but it's application-based. And the idea is that you can apply to accredited universities. So the US government, I think the NSA specifically, does accreditations that say these universities meet a cybersecurity curriculum. And if you are admitted to that university and they're a program participant, then the US government very generously pays for your entire education. You also get, so that means tuition, room and board. You even get a stipend for books. And I would use my stipend every year. I bought a lot of books. I love books and had the chance to read quite a few of them. And in exchange for that support, you have what's called a service obligation. So you go on to a career in the public sector. I had the opportunity to attend Carnegie Mellon University, which is a fantastic school. It was really when I say it was a life-changing education, I really, truly mean that. And there I got into reverse engineering, program analysis, and systems programming. And afterwards, to fulfill my service obligation, I joined what we call an FFRDC. So that's a federally funded research and development center. And I did both applied research, so assessment of specific systems, specifically certain military systems. And I also did academic research. So I had the chance to work on tools, program analysis tools to help scale security assessments. And that is not quite the same as a formal methods correct by construction type job, but we use a lot of the same techniques. So we use symbolic execution, some model checking, coverage guide fuzzing, things of that nature.
Okay. I mean, what kind of things are actually involved in the application? What do you need to do? Do you need to take a specific kind of courses before you even can apply to this?
Yeah. So the purpose of the program, are you talking about the SFS program, the Scholarship Service Program, that application?
Yeah, exactly. That one.
Oh, yeah. So that's a workforce development initiative. So it's really designed to address the shortage in the cybersecurity workforce. So as you probably know, tech skills are generally in demand. It's hard to hire software engineers. And it's also very hard for the US government, I'm sure other governments, to recruit cybersecurity engineers for their missions and their departments. So the idea there is that the only qualification, I believe, is that you have to be a US citizen and you have to be admitted to a participating university. So if you're a citizen, whether that's by lottery or naturalization or what have you, you can apply, and then the requirements for the actual university program are university specific. So usually for a technical graduate degree, they assume that you have a technical undergraduate degree or work experience or relevant background.
Okay. But that's a pretty life-changing event, right? I mean, that you kind of won double lottery, no? Because you got the lottery to come to US and you got this kind of lottery, which is so you must be really lucky, no?
Yeah, I feel very lucky. I feel like in life, you might have a plan and sometimes things go according to the plan. Sometimes new opportunities come along and if you're open to them. But yeah, I feel extremely privileged to have received that education and I really try not to waste it. And a part of my motivation for the book and making the book completely free and available online is to pay it forward a little bit because I know that not everyone will have the chance to attend a graduate program, but there's a lot of people that are self-taught and that are interested in very technical things. And my background specifically, I spent a lot of time doing research and, publishing some research papers, going to research conferences. And what I found is that that community is very insular and exclusive. So if you go to a research conference and you give a talk, usually the people in the audience are kind of the people whose work you've cited, which makes sense, right? Because it's kind of by experts for experts. But there's so much interesting and cool work that just doesn't ever leave that space because, these papers are dense, they're math heavy, like they kind of assume that you're already up to date on all the other advances in the space. So my goal with the book was to kind of take some of that principled, these fundamental computer science concepts, these fundamental computer architecture concepts, these fundamental computer security concepts, and frame Rust in that context in a way that's hopefully more accessible and kind of more engaging and is more open, right? Is more available to more people.
So when you got out of school, you actually already started to work off that. So you graduated, and I think you said you were working for the government, right, for a short amount of time.
Yeah, for several years, about 5 years. So the way it works is you have to apply and interview for a job, same as any other job. You're not actually guaranteed placement in the SFS program, which is fine because tech jobs are plentiful enough to where I don't know of anyone that had trouble fulfilling that obligation or landing a position afterwards. And each lab has a different interview process and different criteria. And these research labs they're very cool places to work because they do applied work. So a lot of the kind of stuff that we do is we have a government sponsor and they have a specific problem. And there's no what we call COTS, so commercial off the shelf. There's no existing solution for that particular problem. They can't pull some open source code in or they can't go to a startup that sells them something. They actually need a custom tool developed. So we can do, we have like 3 to 6 month timeframes where we deliver a working prototype for their need. And then should it be successful, there's like tech transfer and they can kind of transition to another entity to do kind of more of the software engineering and commercialization. But we also get to do long-term academic research. So these are things that a private company just doesn't have the risk tolerance for. So you can look at really, really hard problems, think about them for a very long time, make progress, be able to share that knowledge through open publication. And you have really interdisciplinary teams. So you'll have a pure mathematician, somebody with a PhD in math, sitting next to a systems programmer or a reverse engineer, and they're kind of combining forces to work on these difficult problems. So I think from that perspective, government labs are kind of a special and awesome place to work.
And through here, you said you got like kind of into all this kind of justifiable software, right? Or the trustable software.
Yeah, so that it's in that experience. So the team I worked on, we did a fair amount of what we call system assessments. So you have a system that should be high assurance, right? And the approach we take is we want to trust but verify. So the manufacturer said, hey, we know how to write C really well, and we're following certain industry safety standards. So we're delivering something that is correct, right? And then the system owner comes to us and says, well, okay, we need to test this. We need to sometimes there's a legal mandate. So there's either a congressional line item that allocates budget for this, or there's an executive order for testing the cybersecurity of critical infrastructure, things of that nature. So there's an impetus for us to actually verify that that system is as high assurance as we believe it is. And that's part of the applied assessment work. But the problem, or not the problem, I guess, that the challenge in that space is that if you think about the US government, or probably any government, we're really responsible for securing a wide array of assets. So, embedded systems that are very heterogeneous in terms of instruction set architecture, operating systems, kind of fundamental design. So there's a challenge in scaling these kind of security systems because there's not that many, or the talent pool of skilled security engineers is relatively small, and there's more and more code being written faster and faster. So we really need ways to kind of tame this problem. And this is the same in private industry, right? This is why companies that sell security tools exist. So the other kind of work that we would do is develop tools to scale these assessments and to actually enable certain kinds of verification of various embedded systems.
And so you took this knowledge that you gained working with the government and you were able to actually put this together to something that's other people could do, kind of follow, right? Like through like using these open source tools such as the fuzzing, the compiler, the RRU, the time travel compiler, and also the, is it QEMU? Is it QEMU?
Yeah, so Kimu is a whole system emulator. So it creates a virtual replica of a full embedded device, including all the underlying hardware end to end. And then you have the ability to do arbitrary introspection into program state, which is really, really helpful for certain kinds of verification. And to backtrack slightly, I do want to say that the book doesn't include anything I specifically learned within a government or a classified context. I just have to kind of caveat that. But because I have spent a lot of time thinking about software security in some very serious settings, and I've also had the ability to do open academic research in that area, I'm trying to take a lot of that knowledge and kind of repackage it in a way that's more digestible and more accessible and also just practical for a day-to-day developer, for any Rust developer to be able to apply to their own products and workflows. Because I think most of us as developers strive to build reliable and secure systems, right? We take pride in the work we do and the code we put out. And, we're working under timelines, and it's not always possible to get everything totally perfect. We can't fully verify stuff end to end because we need to ship it. But there's definitely steps we can take to have more confidence in the software and the products that we produce.
So I just kind of want to go over, like, what I understand is that the memory safety of Rust is definitely something that makes it very assurable, right? Or very justifiable or trustworthy, right? Is there anything else within Rust that actually helps with that too?
Yeah. So there's two things that I would point out as really important features of Rust that I think maybe don't get enough coverage. The first is its error handling story. So for high assurance software or just any software that you consider to be reliable, it's actually very important how you detect and respond to errors. And Rust has kind of a major advantage over other systems languages in this category. So if you think about C, the way error handling is typically done is you have an implicit encoding of an error state in a return code. So you return something like -1 from a function as opposed to the integer that it's supposed to compute. If an error happened, you also have this global error state thing called error node, this error number, which because it's global, there's potentially some issues there in terms of multi-threading. But the idea is that in the C language, errors are not actually explicitly required, or there's no way to enforce that errors are handled. So you have standards like MISRA-C, these kind of safety critical coding guidelines that say, okay, the programmer needs to check every return code and act appropriately. But that's not actually something that's fully enforceable. Static analysis tools help, code review helps. But in Rust, when we talk about the result type, which is, I'm sure you're familiar, just type in the standard library, it's marked with an attribute called must use. So it essentially makes error handling mandatory. You need to match on it, or you need to unwrap it, or you need to take some action. So if you're talking about a large code base that has a high amount of complexity, you're actually able to systematically enforce error checks in Rust. And I think that's huge. That's absolutely huge. And I don't know that I'm going to say it's as big a deal as memory safety, but I think it's something that we should definitely consider. And it becomes especially interesting when you compare that to C++, because C++ you can throw an exception. And that is kind of like a result that's mandatory for someone to catch it. It could be a handler in your program, it could be the OS itself. But the problem there is that then you have these kind of invisible exit points within functions. So the exception could bubble up from something that's super, super deeply nested. And that has problems for reasoning about the exception, that has problems for kind of the runtime support needed to handle that. And there's one more thing I want to say about that. It slips my mind. It's in a multi-thread context, there's a global lock used in C++. So if you're throwing a bunch of exceptions from different threads, you're actually slowing down to the speed of a single thread of execution. But in Rust, you have mandatory ways to mandatorily enforce error checking. It's in band. It's not this out of band extra flow exception thing. So that's one reason. And then the other thing that Rust is really strong at is the concurrency story. So because of the type system, which guarantees that reference can be shared, X or mutable, right? So you can only have one mutable reference that's live at any program point. This actually is what prevents data races, because you can statically solve using the type system what we typically think of as like a readers-writers concurrency problem. And there's a readers-writers lock in Rust, by the way. We have like traditional concurrency primitives available in Rust. But essentially, you can avoid data races entirely, not all race conditions, so you can still have deadlock and other things. But that is also very important for reliability, because race conditions and data races in particular are very hard to replicate and very, very hard to debug. So you may hit one like once in a blue moon, and you may never be able to hit that again. But then you deploy a system to production, and you don't have the guarantee that that system at some point will hit that weird miraculous state and have an issue.
I mean, it sounds like a lot of positives for Rust out of the box, but there must be something that's negative about it in terms of guaranteeing this kind of, what do you call it, the high assurance, the justifiability, right? Or else you would just not need to say anything and just say, okay, just use Rust and you're done.
Yeah. So There are a couple negatives. I think we mentioned one, which is the lack of a specification, and that's being worked on by the Ferrocene project. There's also efforts for certified compilers. So that negative is, I think of it as more of a regulatory negative as opposed to a technical negative. And there are people that are working on pushing on that front. The other two negatives I would probably mention are this idea that we talked about with panics. So when we think of high assurance software, it's not actually acceptable to panic. So a panic is preferable to like memory corruption, and because it's kind of the program doesn't die a violent death because it was exploited or memory was trashed. It's kind of a controlled termination. But a termination is still very much not okay in many, many contexts, right? So if something goes offline and it's steering, say, like a vehicle, or it's involved in some operation where there might be a risk to human life, you can't just fail. So the way the book addresses that is through introducing both differential fuzzing, and fuzzing in general is a way to stress test your program, especially this newer kind of variant of fuzzing called coverage guide fuzzing. It actually generates inputs that see more and more of your program. So you can have, you keep running the fuzzer for a longer time, and there's some limitations here, but you can be assured that more and more of the program is covered and that you're more likely to find panic cases kind of probabilistically or stochastically. And then these other newer tools in this deductive verification side of things that we mentioned earlier, they actually have the ability to prove the absence of a panic in certain cases. So you can actually have a kind of mathematical proof that says this function actually will not panic at runtime because the invariants are met such that the panic will never be triggered. So I think that's an important part of assurance that Rust does not solve out of the box. And this is where tools like fuzzing and like deductive verification come in. And then the last weakness that I want to mention is something called stack safety, which we might have alluded to a little bit earlier. But in Rust, so if you think about a buffer overflow, like we talked about, Rust prevents that, specifically with runtime checks. But then there's this other kind of memory problem where if you define a function recursively, the compiler, when it compiles that recursive function, it doesn't know like the largest size, all the possible inputs that function will take. So you could have something where you're recursing many, 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 many stack frames, at which point you might hit a platform-specific limit. So on x86 systems, there are these things called stack probes that the OS can actually detect the stack overflow and respond to it. But on a lot of embedded systems where Rust might be deployed, these other embedded architectures, you don't have that same kind of detection mechanism. So it's possible to use safe Rust, have a recursive function, and then actually still overflow the stack, at which point, depending on what that platform looks like, you could be overwriting code, you could be overwriting data, you could be overwriting something that is assumed to be permanent storage. So it could get very, very bad. And this is where these kind of high assurance coding standards actually require that you don't use recursion, because there's actually advantages to that in terms of execution predictability anyway. But in Rust, it's particularly important because, again, in safe Rust, you're not actually getting stack safety out of the box on a lot of embedded platforms.
Okay, it's learning a lot today. It's maybe getting a little bit over my head at some point, but no, it's definitely interesting. This kind of topic seems to be, it's just like never ending. We may need to schedule another kind of follow up, maybe more towards the end of the book, and talk more about this kind of stuff because it's pretty deep.
Yeah, I mean, security and security research is a very deep space, and there's a lot of exciting work going on. So I'm kind of excited to see how a lot of the projects that I'm monitoring progress and how the certification and specification work kind of pans out going forward.
Actually, maybe we can kind of stop over here for now, just due to time constraints. But since you kind of are in that community, and I think there must be more than one person out there who may also be interested in this. If I were actually interested in this space, is there certain places that I should be looking or certain conferences I should be attending to actually kind of get up to date to what's actually going on in this space?
Sure, yeah. So I think a great source of information is there's actually an interest group, which is different than a working group. I'm not exactly sure how, but there's this Rust Formal Methods interest group, and they have a Zulip channel and a website. And there's regular meetings where people are discussing advances in the formal verification of Rust. And these meetings get recorded and are up on YouTube, on a YouTube channel. And I believe there's also a Twitter account called Formal Ferris that retweets these things. So that's one way to stay involved. I think Ferrocene, which is a private company that I'm not affiliated with, I believe they have a mailing list. So I think that's one way to stay on top of those efforts as well.
Yeah, I mean, besides, if you guys are interested in reading and checking out his book, go to highassurance.rs, and that will be basically the running copy for now. Is there anything else you wanted to say before we sign off?
I did want to mention that the book is open source, and I would really appreciate pull requests for typos or factual errors. So it's something that hopefully can be sustained health-wise in the long term.
Maybe we should settle the score right now. Do you or do you not use a comma before the and if you're mentioning 3 or more things?
So I like to insert commas. Not, I don't want to say arbitrarily, but I feel like I just need a delimiter, and compiler's background. I think any delimiting token is really nice, but maybe that's not grammatically correct. I will look into that.
I think I remember hearing about this online somewhere, that there was a way that these taxi cab drivers in New York were able to get around some issue because there was a missing comma before the and somewhere. I wish I could remember the story, but if anybody's at home interested, there's an interesting story about this. And so apparently most layers do prefer that because of that specific reason. I wish I could figure out why the hell that is, but so I also prefer the comma before the and. It just makes it very clear. So
Right, well,
okay.
thank you. It was a pleasure being on the podcast. Hopefully, some of what I said made some sense.
Yeah, it does. It's just like it's really end of day for me over here after a long day. And so it's like, okay, I'm getting most of this stuff, but I need to kind of soak this in and think about it for a second. It's hard to kind of soak it in and think about it and try to also keep the conversation going at the same time. So I really need to think about this some more. And I think reading your book will definitely give me some more understanding. I mean, you do kind of go over a lot more stuff, like more in depth within your book, I would assume, right?
Yeah, of course.
Okay. So we're all treated as just normal layman people within the readership of the book, right? Within the audience.
Yeah, so the major goal of the book is definitely to be accessible, and that's something I'm constantly working on and also open to feedback to. So there's an email list in the book, and if something is not clear, I will do my best to iterate on it and to improve it, because the long-term goal is to really have like a high-quality free resource that a lot of people can benefit from regardless of their background, so long as they're interested in these topics. And I think there's a lot of interest around Rust right now, so I think it's more and more people are jumping on that bandwagon, and I think that's great for software security.
Yeah, everybody wants to be safe, everybody wants to be fast, but it's a lot of effort involved with making that happen, especially the safe part.
Right, it's not easy.
Fast is easy. I just remembered like this like cartoon of this guy like interviewing. He's getting interviewed, and they said, "What are some of your skills?" And the guy says, "I can do math very quickly." Okay, what's 1+1? And the guy's like, 50. That's nowhere near correct. Yeah, but it's fast, right?
Yeah. And there's a lot of like algorithms and stuff where they apply that same technique where they'll approximate, and in a lot of cases it's good enough. Like that's kind of how machine learning works. I mean, I don't really know how machine learning works, but yeah, I think approximation is pretty decent in some cases. Not in safety critical, right? You definitely need to be correct like more than 99% of the time, right? Because that 1%.
That's basically when you work with floats, right? Is that if there's single point floats, it's like, the famous 0.01 plus 0.02, you're going to get a very weird number coming out. But that's just the way floats work.
Yeah, floating point encoding is its own weird thing, and there are some really good people working on optimization and speed there. I think that there have been contributions to the Rust toolchain around improving the floating point flexibility and speed.
Okay. Again, thanks for your time. It's fantastic having you on. I'm looking forward to cracking open this book and seeing how it goes. And yeah, maybe I'll have you back after the end to talk about, I'm sure you're going to be learning quite a bit more, because when you have to actually start teaching something, you have to learn that thing even more than you thought, because you're going to get some very interesting questions as you're writing the book, right?
Absolutely. Writing forces you to both deepen and refine your understanding in a very, very serious way. So, yeah, thank you. It's been a pleasure.
All right. Thanks again.